Hello students, in this video we are going to know about the planar graphs. Let us consider a complete graph of 4 vertices, K4. So you know how to draw the K4. It has 4 vertices and each vertex is of degree 3. So if I name the edges as E1, E2, E3, E4, E5 and E6, so you can see that there is a edge crossing. So there is a crossing of edges E5 and E6. The same graph K4 can be written as shown here. So K4 can be written with 4 vertices, E1, E2, E3, E4 edges and E5 edge, and E6 can be written from outside. So now in this graph you can see that there is no edge crossing, and such a graph is called a planar graph. Now let us define a planar graph. A graph G is called a planar graph if G can be drawn in the plane so that no two of its edges cross each other except at the vertex. So a graph that is not planar is called non-planar graph. So hope it is clear now what is a planar graph and a non-planar graph. So this K4 can be written in the form of a planar graph as there is no edge crossing between E5 and E6 in figure 2. Now let us consider these two graphs G1 and G2. You can see that G1 is a graph with 5 vertices and all the 5 vertices are connected. Now you have another edge here and you can see that in G1 there is no crossing of edges. Hence G1 is a planar graph. G2. If you see G2, it is again a complete graph K5. It is K5 and we know how to draw K5. So let us just check whether K5 is a planar graph or not. So again let me draw the graph. I'll first join these edges. So you can see that there is no crossing of edges. Now I'll draw this edge. Okay. Now if I try to draw this edge, there is a crossing of edges. So I cannot draw this edge. So what I'll do is I'll draw an edge like this. Now there is no crossing of edges. Now I am done with this edge and this edge. We are left with 2 more edges. Again, instead of drawing an edge connecting these 2 vertices, if I draw the edge from outside, again there is no crossing of edges. Next we are left with one more last edge which is connecting these 2 vertices. So if I draw inside, there will be a crossing of edges. If I try to draw the edge outside from outside, again there will be a crossing of edges, and therefore it is a non-planar graph. So K5 is a non-planar graph. Now a planar graph divides the plane into connected pieces called regions. What do you mean by regions? They are the connected pieces. So they are the divisions made by the planar graph. For example, you have this graph AB made by A, B, C, D, E. Now you can see that there are regions. There are few bounded regions. R1, R2, R3 are bounded regions, whereas there is an unbounded region R4. So this unbounded region is the exterior region. So let us consider a few more examples here. Consider the cycle C3. So C3 has 3 vertices which are all connected, and this C3 creates regions R1 and R2. R1 is a bounded region and R2 is unbounded region. Next, a graph which is called a tree. Tree is a connected acyclic graph. So you don't find any cycle here in the tree. So this is it is a connected a cyclic graph. There is no bounded region in this graph and it has only one region R1. And you can count the number of edges: 1, 2, 3, 4, 5, 6, 7. There are 7 edges. And how many vertices are there? 1, 2, 3, 4, 5, 6, 7, 8. So one of the characteristics of a tree is, if there are n number of vertices, then the number of edges will be n minus 1. So 8 minus, there are 8 vertices, 8 minus 1, 7 edges are there in the tree. And a tree has only one region, exterior or unbounded region R1. Now let us consider these two graphs. So you can see that in the first graph you have 3 regions, R1, R2, which are bounded regions, and R3 is an unbounded region. So this graph is isomorphic to the graph as shown here. Now you can see that this graph, so if I call this as graph G1 and this as G2, the graph G2 has also 3 regions, R1, R2 and R3. R1 is a bounded region, R3 is an unbounded region. But if you see the regions between the regions R2 between the graphs G1 and G2, there is a difference. So we can say that they are different as planar graphs, but they are isomorphic. Okay, both are planar graphs, but they differ by the regions, but they are isomorphic. Okay, so we have seen that here the K5, the complete graph with vertices 5 is a non-planar graph. Now let us consider a complete bipartite graph K3, 3. You know how to draw K3, 3. So the 3 vertices in one set are represented with black color, and 3 other vertices with blue color, and the connectivity, the edges are shown here. Now I want to just see whether this can be written as a planar graph. So for that, since there is no connection between any two black or any two blue vertices, I will draw the vertices in such a way that they will appear in the alternate positions. So black, blue, black, blue, black, blue vertices. So there is always a connection between black and blue. So I can show this with the edges. So black connected with blue, blue with black, black with blue, like this. So the outer region boundary is over. So there are totally 9 edges here, right? There are 9 edges. Now 6 have been covered. Now I have to connect black with other blue. Black with the next blue is this. So I have an edge. Next, other black with the remaining blue is this. So if I draw an edge like this, there will be a crossing of edges. So I can draw the edge from outside. I can draw the edge from outside, so which is not crossing over. Now I have to connect the other pair, black with blue. So for which I have to either draw it from inside. Again there is a edge crossing, or if I draw it from outside, there will be an edge crossing. And therefore, so if I cannot draw the K3, 3 as a planar graph. So K3, 3 is not a planar graph. Now consider the following graphs. So we can observe some commonality between the planar graphs. So we have this graph G1 and graph G2. Okay, so this graph G1 is a connected graph which has regions R1, R2, R3 and an exterior region R4. So if you count the number of vertices V, which is equal to, usually we denote it by N, that is equal to 7. Number of edges 1, 2, 3, 4, 5, 6, 7, 8, 9. So number of edges E or M is equal to 9. Number of regions R or small r is equal to 4. So if I consider n minus m plus r, that is number of vertices minus number of edges plus number of regions or faces is equal to 2. Now consider the graph G2. You can see that it is a connected acyclic graph which we call it as a tree. It has only one region R1. So number of vertices here is n equal to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Obviously, since it is a tree, number of edges E or M will be n minus 1, that is 11. And number of regions R is equal to 1. So n minus m plus r is equal to 12 minus 11 plus 1, which is equal to 2. So in general, for any connected planar graph, we have n minus m plus 2 r is equal to 2, or vertices minus edges plus r is equal to 2. So this is a relation which is true for all connected planar graph, and this is called the Euler identity, and Euler identity is stated as a theorem and the proof is provided. So the statement of Euler identity is this: if G is a connected planar graph of order n and size m and having r regions, then n minus m plus r is equal to 2. So we shall prove this theorem by induction on the number of regions R. So now in the step 1, let us consider that the result is true for R is equal to 1, or if R is equal to 1, let us prove the result for R equal to 1. If R is equal to 1, then G cannot be a cyclic graph. So that means G cannot contain any cycle. And since G is connected, G should be a tree. And a tree with n number of vertices has n minus 1 number of edges. All these things we have seen in the example. And therefore, and it has only one region R. So n minus m plus r is equal to n minus of n minus 1. In place of m, it is n minus 1 plus 1 equal to 2. So thus we proved the result for R is equal to 1. Now let us assume that the result holds good for all graphs with R greater than or equal to 2. Okay. Now in step 3, if R is greater than or equal to 2, then G is not a tree. That is obvious because there are more than one region. If there are two regions, then there should be some cycle. It cannot be a tree. And hence it has cycle. And in a cycle, there will be a common edge which divides the regions, right? So let E be an edge on the cycle, and E is on the boundary of the two distinct regions. For example, if I'll just draw it here, let us consider a graph something like this. So you can see that there are two regions R1 and R2. There is an edge. There is an edge. If I remove this edge, then it becomes single region, right? So it becomes like this, right? It has only one region R dash. So similar situation is considered here. So E is an edge on the boundary of the two distinct regions R1 and R2. By removing the edge E, the two regions R1 and R2 merge and form a new region R dash. Since G minus E is now has M dash, which is equal to, just I removed one edge. So the number of edges in the new graph will be M minus 1. And the number of regions in the new graph formed will be R dash, which is equal to R minus 1 region. So only one region is going to reduce here. Now applying the inductions hypothesis, we get 2 G dash is equal to G minus E. We have for a G dash, the number of vertices remains the same. So it is n only. Number of edges will be m dash and number of regions will be r dash. So this is equal to n minus of m minus 1 plus r minus 1. So that gives you 2. So we assumed that the result is true for all r greater than or equal to 2, and just by removing an edge we got one region less, and hence we are getting the result proved. We also have theorems which gives the condition for the planar graph. Okay. So if G is a planar graph of order n greater than or equal to 3 and size m, then m is less than or equal to 3n minus 6. So if the graph is a planar graph, then m will be less than or equal to 3n minus 6 provided there are triangles. That is, it has 3 cycles. Then second condition, m is less than or equal to 2n minus 4 if G has no 3 cycle. Okay, this first condition is for 3 cycle and second condition is for no 3 cycle. So this theorem can also be written in this form, the condition for non-planar graph. If G is a graph with n greater than or equal to 3 and size m greater than 3n minus 6. So it is the negation of this condition, m less than or equal to 3n minus 6. So m greater than 3n minus 6, then G is a non-planar graph. Then the second point, if G is a graph with no triangles, so it is the negation of the second condition of this theorem. Okay, with no triangle and m greater than 2n minus 4, then G is non-planar graph. G is non-planar graph. Now we have another important theorem which states that every planar graph contains a vertex of degree 5 or less. I'll repeat, every planar graph contains a vertex of degree 5 or less. It cannot be more than 5. So let us prove this theorem by assuming the degree of the vertex to be more than 5 and prove that it is non-planar. So suppose G is a graph with every vertex of degree 6 or more, that is greater than 5, 6 or more, which implies that the number of vertices must be greater than or equal to 7. So for a graph of vertex 7, for a simple graph of vertex number of vertices 7, the maximum degree of each vertex can be 6. So we are considering a graph G with every vertex of degree 6 or more, which implies that n is greater than or equal to 7. And we have from the theorem that the sum of all the degrees of the vertices is equal to 2 times the number of edges. So 2m is equal to summation degree of u, where u belongs to vertex set of G, and this should be greater than or equal to 6 times n. So this is the minimum value of the minimum degree that we are considering is 6. So it should be 6 times n, right? Thus m, so now you have a 2m greater than or equal to 6n. So this can be written as m greater than or equal to 3n, or m is greater than 3n minus 6. So when it is greater than or equal to 3n, I am just removing some some number, positive number from the right hand side. So obviously it should be m greater than 3n minus 6. Hence G is a planar, non-planar graph. Hence G is a non-planar graph, because we have seen the condition for a non-planar graph, that is, if m is greater than 3n minus 6, then G is a non-planar graph. So therefore, if G is a planar graph, then G contains a vertex of degree 5 or less. So there is one more theorem which states that the complete graph K5 is non-planar. So this is K5, this is K5, and you can see that there is a 3 cycle here. The graph contains a 3 cycle. So therefore, which condition I have to apply? I need to check whether m is greater than 3n minus 6 or m is less than or equal to 3n minus 6. So if m is greater than 3n minus 6, then the graph is non-planar. If m is less than or equal to 3n minus 6, then the graph is planar. So here in this case, K5, number of vertices n is 5 and the number of edges is 10. So if you consider 3n minus 6, it is 15 minus 6, that is 9. So 10 is greater than 9. So this implies that K5 is non-planar. Even we proved this by trying to draw this graph without crossing of edges, which is not possible. Hence it is non-planar. Now the complete bipartite graph K3, 3 is non-planar. So here again let us consider this K3, 3. So you can see that there is no triangle here. You can see you have a two edges of a triangle, but the third edge is not there. Okay, so this is a graph with no cycle, no triangle, and no cycle of degree 3. So therefore in K3, 3, n is equal to 6 and m equal to number of edges is equal to 9. So 2n minus 4 is equal to 12 minus 4, which is equal to 8, and therefore 9 is greater than 8. And this implies that K3, 3 is non-planar. Also we have just tried drawing this K3, 3 without edge crossing, which is not possible. So that also shows that K3, 3 is non-planar. So next, how to check whether a given graph is a planar or non-planar. So before going to the condition for the planarity or the step-by-step the procedure for checking whether the given graph is planar or non-planar, first we need to know what is called as the homeomorphism. So what is homeomorphism? Two graphs are homeomorphic if they can be transformed into each other by a series of edge division. That is, what is edge division? Adding a new vertex to an existing edge creates a subdivision of that edge. So this can be easily understood with this example. Let us consider two vertices connected by an edge E. UV connected by edge E. I will introduce another vertex W, right, between U and V or on the edge E, which divides the edge E into E1 and E2. So both the graphs, these are graphs, right, are homeomorphic, right? So just by introducing an edge, introducing a vertex, the edge is divided into two parts, E1 and E2. So, but these two graphs are homeomorphic. Now let us consider graph G and H. Okay, now you can see that in graph G there are 5 vertices, right? In H there is a division of this edge. I have introduced the vertices on all the edges, on the outer edges, and the vertex here has been removed from this edge, right? Whether you add the vertex or delete the vertex, right, we get the graphs which are homeomorphic to each other. So here graph G and H are homeomorphic. Okay. Now we are going to give a condition for the planarity of the graph. So the graphs, the complete graph K5 and the complete bipartite graph K3, 3 are the Kuratowski graphs, right? And the theorem states that a graph G is planar if and only if it has no subgraphs homeomorphic to either K5 or K3, 3. I'll repeat, a graph G is planar if and only if it has no subgraphs homeomorphic to either K5 or K3, 3. So let us consider the Peterson's graph as shown here in this figure, and this is homeomorphic to K5. How? See, we have the you can see that the vertex, okay, let me just label these vertices A, B, C, D, E, F, G, H, I, J. Okay, now A, F, H can be considered as an edge by just removing this vertex F, right? So if I just remove the vertex or edge, if I remove the edge AF, so it becomes coinciding with this, the edge BA now becomes BF, right? The edge BA becomes BF, and again similarly if I remove BG, I'll get this BF now coinciding with GF. So it becomes F, G, H, I, J. Is that clear? Just by merging the edges, we get the graph, Peterson's graph, homeomorphic to K5. And therefore, we know that K5 is non-planar, and therefore this Peterson's graph is also non-planar. Now let us consider this graph. You can see that on every edge there are few vertices, and those vertices are dividing the edge into subdivisions. So if I remove those extra vertices, I'll get K3, 3. See, I have removed these two vertices from this edge, and I'll get one single edge. Similarly, if I remove this edge, I'll get this edge vertex. This edge I'll get. So like this, if I remove all the extra vertices, I'll get 3, 3, and therefore this graph is homeomorphic to K3, 3. Therefore, the given graph is non-planar. Okay, so these may be very simple ones to just check whether it is planar or non-planar, whether it is homeomorphic to K5 or K3, 3. But in practically it's not that easy. So the graphs may be very complicated. So in such case, we use an algorithm called the elementary reduction algorithm to detect whether the graph is planar or not. So now let us see step by step procedure. To check whether a graph is planar or non-planar, we follow the simplifying steps. So in step 1, suppose if you have a disconnected graph, then we should check whether each component are planar. So disconnected graph means, suppose I have a graph like this, something like this. So there is no connection between but this entire thing is a graph, but they are disconnected. I need to check whether each graph is planar. Each component is planar. If each component of this disconnected graph are planar, then the graph is said to be planar graph. Then also a separable graph is planar if and only if each of its blocks are planar. So let me consider this graph. It is a separable graph because I have two blocks here, one triangle and one square, right? So two blocks are there, and if both the blocks are planar, then we say that the entire graph is planar. So therefore, for the given arbitrary graph G, determine the set G equal to G1, G2, G3, etc. Gk, where Gi is a non-separable. So there cannot be, see here I have separated the blocks. These blocks cannot be further separable and they are called non-separable blocks. So Gi is a non-separable block of G. Then we need to check if each Gi is planar. Now step 2. Since addition or deletion of self loops does not affect the planarity, remove all the self loops. In self loop there is no edge crossing, and therefore just by removing the self loops the planarity remains the same, and hence we remove all the self loops. That is step 2. Step 3. Since the parallel edges also do not affect planarity, parallel edges in the sense I have an edge like this and an edge like this, right? They are parallel. So they have they are connected between the same two vertices. They are parallel edges and they won't affect the planarity as there is no edge crossing. So eliminate such parallel edges, removing all except one edge. One edge should be kept as it is. Next, step 3. Elimination of a vertex of degree 2 by merging two edges in series does not affect planarity. Again, for example, you have an edge like this which has another vertex like this. So the two edges E1 and E2 are in series. So just by eliminating this vertex, I'll get only one single edge. So this won't affect the planarity as there is no edge crossing. Therefore, such series edges can be removed, or vertex of degree 2 can be removed. See, this is a vertex of degree 2. Such vertices can be removed. Therefore, eliminate all edges in series. Repeat this application of steps 3 and 4 with repeated application of this will reduce the graph drastically, and it will simplify to some graphs which either contains only two vertices, or it may be K5 or K3, right? So based on that you can say whether the given graph is planar or not. Now let us consider this example. Let us consider the graph. You can see how complicated it is. It's not easy to check the planarity by the homeomorphism or by any other formula, right? So we use what is called as the elementary reduction algorithm here. So in the first step, what we are going to do, you can see self loops here, right? So remove all the self loops. By removing all the self loops, we get this graph. You can see that the loop here, and here has been removed. Next, what is the next step? Remove all the parallel edges, right? So you have two vertices here which are connected by two edges. Okay, so those are called parallel edges, and thus that can be removed. See, that has been removed. Next step, removing the edges in series. Removing the edges in series. That is, see, you have the edge connecting, an edge connecting these two vertices through this vertex, right? So we call this edge and this edge are in series, and that can be removed. So this vertex can be removed and we get a single edge. Similarly, this is a vertex, this is an edge in series, and that can be drawn as a single edge. So we get this. Now it has converted to parallel edges. Again you remove the parallel edges. So you remove this and these edges. We get this. Now you can see that this graph is homeomorphic to K5. You can see that you have a graph here, subgraph, which is homeomorphic to K5, right? So this implies that this graph is non-planar. Again, I'll repeat this theorem which states that a graph G is planar if and only if it has no subgraphs homeomorphic to either K5 or K3, 3. No subgraph. You should not find a single subgraph which is homeomorphic to K5 or K3, 3. And you know what is a subgraph? So this has a subgraph which is homeomorphic to K5, and therefore this is non-planar. So we'll check whether this given graph G is planar or non-planar. So follow the steps. First you remove all the self loops. So we get this graph. Then you remove the parallel edges. You have a parallel edge here, you remove that. Then you remove the vertex of degree 2. So this is a vertex of degree 2 that can be removed. So you will get only one edge. Then again this is parallel. You remove that. Parallel edges, remove. And then you have again vertex of degree 2 and 2. So that can be removed and just draw one edge like this. Again you have 3 parallel edges. You just remove the 2 parallel edges and just a single edge you will get. So this shows that the graph is a planar graph. This graph is a planar graph. Is that clear? So we can solve few more problems to understand the concept of planar graphs. Thank you.